G'day guys, today I'm going to take you through the Wiggers diagram. The scope of this short video will be to briefly look at the history of the Wiggers diagram and look at their use as well as other pressure diagrams of the heart. The Wiggers diagram was the work of Carl J. Wiggers MD. It is important to note that Dr. Carl was an academic physician scientist rather than a clinical medical specialist, which gives a very strong hint as to the use of the diagram, which was named after him. The diagram was first released in the now ironically named 1915 book Modern Aspects in the Circulation in Health and Disease to aid in teaching students the cardiac cycle, and it has been updated over the years to its current form. So let's break down the different elements of the diagram as you will see it. Firstly, you'll note multiple lines on the diagram that are broken down into pressure, volume, ECG, and sound elements. You'll note by the pressure ranges that the diagram is focused on the left side of the heart, although a similar diagram could be drawn for the right side of the heart. Noting how much easier it is to measure arterial blood pressure, the reason for this should be evident. So when we break down the pressure lines, we have the aortic pressure in red, left ventricular pressure in blue, and left atrial pressure in yellow. These are important when we consider that fluid will flow from the high to low pressure in the same way water moves down a hill. So noting the pressure gradient between the components of the heart, which are connected by valves, is important. By looking at the ventricular pressure, we can determine systole and diastole. For interest, systole and diastole come from Greek and Latin origins, where systole is to contract and diastole is to expand. Unfortunately, knowing this etymology will not help you very much learning these words. So, looking at the diagram, we have systole when the ventricular pressure increases, and obviously diastole, the pressure will drop as the heart relaxes. The start of systole aligns to the R wave in the QRS complex, and the end occurs somewhere in the last third of the T wave, noting variance between versions of this diagram and the health of the heart. So when we move on to the specific phases, they are as follows. Starting at the start of systole, we have the isovolumetric contraction. Firstly, the pressure in the ventricle rapidly increases and becomes greater than the atrial pressure, causing the mitral valve to shut, causing the first heart sound. The pressure in the ventricle continues to increase until the pressure is greater than that in the aorta, at which point the aortic valve opens, ending this phase. As all valves are closed during this phase, the ventricular volume does not change. Following this, we have the ejection phase. As blood is ejected from the ventricles, the ventricular volume drops. During this phase, the ventricular pressure increases, then decreases, and when it is less than the aortic pressure, the aortic valve closes, causing the second heart sound. Following this, we have diastole, which is broken down into a number of subphases. The first of these is isovolumetric relaxation. As the pressure in the ventricle is less than the aortic pressure and greater than the atrial pressure, all valves are closed and the ventricular volume does not change. As soon as the ventricular pressure is lower than the atrial pressure, the mitral valve opens and the ventricle rapidly then continues to fill slower. Lastly, the atria contracts, and that atrial systole is seen by an increase in pressure in the atrium. Note the correlation between this and the P wave. It is important to note that pressures will drive the flow of blood and the closure of the various heart valves. A schematic of where the valves are open and closed in the phases has been added to the diagram along the bottom for clarification, showing mitral and then aortic. To confirm the heart sounds, the first heart sound is the closing of the mitral and tricuspid valves. In some pathology, this can be split. from 1 into 2 sounds, and this sound occurs during the isovolumetric contraction. The second heart sound is the closing of the aortic and pulmonary valves. This can also be split in some pathology, and this occurs and is heard during the isovolumetric relaxation. The third heart sound is a low-pitched sound caused by the rapid rush of blood from the atrium to the ventricles. It is normal in children, and in adults it is associated with ventricular dilation. And then lastly, the fourth heart sound, which is unfortunately not shown directly on this diagram, occurs just before the first heart sound and is caused by forced atrial contractions in the presence of decreased compliance. It is associated with stiff, low compliant ventricles, so e.g. ventricular hypertrophy and ischemic ventricle. While considering the Wiggers diagram, it is also worth considering the pressure volume loop diagram, which you may also see. It was clearly designed by an engineer to express similar learning points that you would see in the Wiggers diagram. The first thing to note is that time is not represented in this diagram, so the isovolumetric phases are overemphasized. Next, it is important to note that the diagram progresses in an anti-clockwise direction. Second point to note then, moving on from that, is the stroke work, which is the area inside the loop, and it relates to the conventional definition of work being force multiplied by distance. However, the usefulness of this in a medical situation is low due to clear oxygen energy use during the isovolumetric phases. Some key elements will now be highlighted, so you will see where they are represented here. Firstly, we have diastolic pressure and systolic pressure. We have the opening and closing of the mitral valves, the aortic valve opening and closing, diastole on the bottom triangle of the diagram, and systole, and lastly the end systolic and end diastolic volumes. Thanks guys, I hope that this video helped.